Hello, hello, hello. In this episode of What's the Big Idea, we're going to talk about modeling friction. And I have to say at the outset that this is a little bit more of a rant than a full-fledged episode of What's the Big Idea. I just want to talk about what modeling means and to just point out that models are different than fundamental physical laws. And so far we've talked about one type of friction, and it's the case of a ping pong ball moving through air. In that case, we called if the ping pong ball moves to the right at some velocity v, we find that it experiences a force in the direction opposite to v. We call that force the drag force. And then we came up with a model, which was, identified a mechanism for the drag force due to collisions with the air. And we argued that the drag force should be proportional to the density of air, the area of the ping pong ball, the cross-sectional area, and the speed of the ping pong ball squared. And that was just a model. It was based on sort of a theoretical argument. And in the laboratory portion of this course, you're going to test that model. You're going to see how well that model works. Well, similarly, in chapter 5, Wolfson talks about another kind of friction. It's the kind of friction between surfaces, two hard surfaces, and in the case where the surfaces are moving with respect to one another, we call that type of friction kinetic friction. And so a block slides on a table, and if the block is sliding to the right, we find that indeed there's a frictional force pointing to the left. And as Wolfson correctly points out, and image is actually stolen from Wolfson, what's really going on here is pretty complicated. If you look at the microscopic level, there's a lot of uh, roughness at the microscopic level, and the friction arises. You can think of these as little, and there's some contact between the teeth, and they tend to adhere at the contact points. And then as you increase the normal force, the contact increases, so there's a greater contact. This is a very complicated situation, and yet Wilson proposes a very simple model for modeling the magnitude of this frictional force. He proposes that it is proportional to some dimensionless constant mu sub k, which depends on the nature of the surfaces involved, and then the magnitude of the contact force, the normal force rather, the magnitude of the force between the blocks that points in the direction perpendicular to the surfaces. And he argues that, well, we expect the friction to increase as that force increases because the sort of surfaces get squished together. In any event, you can just see from this picture that you're taking a very complicated situation and trying to summarize it with a very simple model. And simple models are all well and good, but the real proof of the pudding is in the tasting, as they say. And you really don't believe any of these models until you go and do experimental tests. My quibble with Wilson and a lot of other introductory textbooks is it turns out if you go and you do experiments, this model of friction, for example, says it shouldn't really depend on how fast the block is moving. And if you go and do experiments and you find out this generally is a pretty lousy model, but I think it's popular in textbooks because you can write textbook problems that you can solve with this simple model. Um, I think you will find experimentally, I don't want to give away uh, the punchline, but this drag model that we developed for a ping pong ball in air works pretty well, all things considering. Whereas the models that Wolfson is proposing in chapter 5 for friction between two hard surfaces are only very, very qualitatively correct. So that's my rant. I think we'll study this section and we'll assign a couple of problems, but I don't want you to be misled into taking these results too literally. When you go out in the real world and you make measurements of friction, you find out that these simple models of friction between sliding surfaces are really not all that great. So that's it for this abbreviated episode of What's the Big Idea? Hope to see you again soon. Bye bye.